Today we're going to use Ampere's law to find the magnetic field produced by a wire sheet that's infinite in space in all directions. Let's set up the problem. We draw a plane, which we'll say is our wire sheet, and it extends to infinity in the x and y directions. We'll put it in the xy plane, and we'll draw our Cartesian coordinate system such that z hat direction is up, our x hat direction is in the plane in this direction, and our y hat direction is in the plane in that direction. And we'll say that our infinite plane here, our wire sheet, has a sheet current, K, and we'll put it all in the x direction. So we'll say that K is our sheet current, and we have the magnitude of K, and it's all in the x hat direction. So the next step is to find out what is the direction of the magnetic field, because after we know this, then we can use an Empyrion loop to exploit the symmetry of the problem and choose the Empyrion loop such that the magnetic field and the Empyrion loop in combination simplify the integral in Ampere's law. So we'll start by drawing in a slightly different way. And instead of having a sheet of current, we're going to essentially break up the sheet into, in this case, 3 infinite long lines of current. And the individual right-hand rule for each line says that we'll put our thumb in the direction of the current and we'll curl around the line of current to find the magnetic field. So the magnetic field will actually curl around like so. We'll do it this way as well for all 3. And so we have the magnetic field curling around each line of current, where the current is I for each one, and the current points around, and we use the right-hand rule to find out the direction. And now what this means is that at the top, the magnetic field will be pointing in this direction, which in this case is the y hat direction, and on the bottom will be pointing in this direction. And what that also means is that at this component here, this line of current will produce a magnetic field that points upwards, and subsequently this line of current at this point will produce a magnetic field that points equal but opposite direction to this one over here. And what that means is that the 2 z hat components from these 2 lines of current are going to cancel. And we're going to end up with having no z hat component contribution from any of these lines of current. So what that means is that there's no z hat component. Of course, there's no magnetic field in the direction of the line of current, so there's also no x hat component. And we're going to be left with only a magnetic field in the y hat component, which will be pointing to the negative y hat direction above and the positive y hat direction below the plane. So here's the magnetic field above, and here's the magnetic field below. And then in this case, we choose an Empyrion loop to exploit the symmetry, so the Empyrion loop will be rectangular, and we'll say that it's like so above, like so below. And we'll direct dl for the Empyrion loop in that direction above and in that direction below. And this will allow it to simplify the integral in Ampere's law. And we'll use this Empyrion loop and this magnetic field in order to find what the magnetic field is for the wire sheet. Now that we have the diagram set up, let's work through Ampere's law in its integral form to find out what the magnetic field is. So we'll start with Ampere's law, which says that the closed integral of the magnetic field dotted with the infinitesimal line element is equal to mu naught times the enclosed charge by the Empyrion loop I enclosed. So we'll start with the left-hand side of this equation, and we'll say that the closed integral of b dot dl is equal to, and by looking here, we say that the magnetic field, of course, is pointing in the negative y hat direction on top of the wire sheet and in the positive y hat direction underneath the wire sheet. And we direct our Empyrion loop such that dl is also pointing in the negative y hat direction on top of the wire sheet and in the positive y hat direction underneath the wire sheet. And what that means is that all points b dot dl is going to be parallel, so that this dot product simplifies to simply be the magnitude of b and times the magnitude of dl. And then of course the vertical components contribute nothing because there's no magnetic field in that direction. So this integral simplifies to become the integral closed of the magnitude of b times dl. And then we can have a contribution from the top and the bottom of this Empyrion loop. So we're going to end up with 2 times the magnetic field times the integral of dl. And we pull this magnetic field outside of the integral because it's constant along the top and constant along the bottom. And by constant, we say it's the same magnitude at all points on the Empyrion loop above and below the plane. And then solving this integral, which is no longer closed because we don't include either side, we can just integrate along the Empyrion loop. And if we say that it has length L, then this integral just becomes 2 times the magnitude of B times L. And we end up with the final solution, which is that the closed integral of B dot dl simplifies down to simply 2 times B times L, where again the 2 came from the fact that we have a contribution on the top and the bottom of this Empyrion loop. To complete the problem, we look at the right-hand side of the equation, where we need to find out what is the enclosed current by this Empyrion loop. So if we draw the Empyrion loop in a way that we can better look at it, so it's not on the wire sheet in the diagram above, we have that the length of the Empyrion loop is L, and the current crossing this Empyrion loop, crossing this surface produced by this Empyrion loop, is of course our sheet current K. So the amount of enclosed current that passes through this Empyrion loop, I enclosed, is going to be the magnitude of the current crossing this surface multiplied by the length of the Empyrion loop, to suggest that the amount of current passing through the loop depends on the length of the Empyrion loop. So what that means is our equation becomes 2 times B times L is equal to mu naught times K, the magnitude of the sheet current, times L, the length of our Empyrion loop. And then if we look at the equation here, of course the L's will cancel, and we can do some algebra to find out what the magnitude of our field is. Magnitude of B is simply mu naught over 2 times our sheet current K. Now, to find out what the direction vector of this magnetic field is, we'll have 2 components. So we'll say that on top of the sheet, on top of the plane, and we'll have a component below the sheet or below the plane. And on top of the sheet, as we said before, we'll have the current in this direction, in the positive x-hat direction, and the magnetic field will be moving in the negative y-hat direction above. So we'll say that the magnetic field is minus mu naught over 2 times k y-hat. And below, we'll have the current, again, in the positive x-hat, and the magnetic field move in the positive y-hat direction. So we'll have that below the sheet, we have positive mu naught over 2 times k